Example 1, we have that a magazine article states that 20% of sports cars are red. John does not believe this article. He thinks the percentage of sports cars that are red is different than 20%. He randomly picks 70 sports cars registered with the tax office, and he finds that 21 of them are red. And we are going to test his theory using a 5% significance level. First, I'm going to identify the information that is given to us in this problem. We are given that P is equal to 20%, so I'm going to write that P is equal to 0.20. From that, I can find Q, because Q is equal to 1 minus P, and so Q is equal to 1 minus 0.20, which gives us that Q is 80%, or 0.80. We are not explicitly given P hat, so we do not have P hat. We have to find P hat, and P hat is X over N. They tell us that he randomly picks 70 sports cars, and so that's our N, our sample size, and of those 70, 21 of them are red. It's our number of successes, the number of red cars. So our P hat is going to be equal to 21 over 70. So what we're doing right now is we're finding our sample proportion. 21 over 70 as a decimal is 0.30. And so now we also have our sample proportion. We need to check two things, that N times P is greater than or equal to 5, and that N times Q is also greater than or equal to 5. N times P is 70 times 0.2, which is equal to 14. That's larger than 5, and so that's good. N times Q is 70 times 0.8, which is equal to 56, which is also larger than 5, and so that is good. You have to check those two inequalities are valid before we can proceed with a single population proportion test. So now we are ready to begin step 1. We will write our two hypotheses. Our null hypothesis, our HO, is that P is equal to 0.20. Notice we're using P and not P hat because we always use population symbols when writing our hypotheses. Our HA, this is what John thinks. John thinks that the percentage of sports cars that are red differs from 20%. So John just thinks that P is not equal to 0.20. And so we have a two-tail test since we have a not equal to in our alternative hypothesis. Now moving on to step 2, we will calculate our test statistic using the formula that Z is equal to P hat minus P divided by the square root of P times Q, all divided by N. P hat is 0.3, and from that we are subtracting 0.2, and then we are dividing by the square root. In the numerator of the fraction that's under that square root, we're multiplying P and Q. So we're multiplying 0.2 and 0.8. That is our P and our Q. And then we are dividing by our N, which is 70. We will round our test statistic to 2 decimal places to get approximately 2.09. So we have our test statistic. Now we are moving on to step 3, where we will determine our critical values. We have 2 critical values here, since this is a two-tailed test, and we will draw our rejection region. We are testing John's claim with a 5% significance level, and so our alpha is equal to 0.05. That is the total area between the two tails. And so the area in one tail is going to be 0.05 divided by 2, because we need to share it between the two tails, which gives us 0.025. That is the area in each of these two tails. And I'm shading them. And these two tails together, the shaded region, comprises our rejection region. Now we must determine what our critical values are. We will head over to our statistics table. We are looking for the z-value. We use the standard normal distribution table for a single population proportion test. So I'm looking for the z-value that has the closest area to 0.0 0.025. So looking for 0.025, that's right here. That is negative 1.96. So negative 1.96. When you have a two-tail test, you can use this section here at the bottom to find your critical values also. Remember, our alpha, our level of significance, is 5%, and so our level of confidence is 95%. So 95% level of confidence, it's right there, that tells us that our critical value is a 1.96. So now we know that our two critical values are negative 1.96 and positive 1.96. Remember, we have symmetry here, so once we find one, all we need to do is change the sign to find the other. We will now take our test statistic of 2.09 and drop that into the picture. 2.09 is larger than 1.96, and so that does land in the rejection region. And so that tells us that when we go to step 4, we will make the decision to reject the null hypothesis because our test statistic did land in that shaded rejection region. So we are rejecting HO, and so we are accepting HA. So now in our last step, we're ready to write the conclusion of our hypothesis test. In that conclusion, we want to start off and mention the significance level that was given to us in the problem. We have a 5% significance level. And remember that in step 4, we made the decision to reject the null hypothesis and accept the alternative. So we are accepting the alternative hypothesis that the population proportion is different than 20%. So our conclusion is that at the 5% significance level, there is enough evidence to support HA that the population proportion of sports cars that are red is different than 20%. Notice how I am giving all this context here that was included in the problem to start off. We do want to make sure that our conclusions are written with context. We also want to make sure that we are mentioning population proportion in that conclusion since we are doing a hypothesis test for a population proportion. Less of cars are pink. She randomly selects 500 cars. She finds that 5% of them are, and we want to test her hypothesis with a significant 0.01. So we are given in this problem that P is equal to 10%, and so that translates as a decimal to 0.10. And so our Q we will find by subtracting that 0.10 from 1 to give us 0.90. Our P hat in this example, we do not have to calculate it like we did in the previous example. We were given the sample proportion in this problem. From her 500 cars that she sampled, 5% of them are pink. And so our P hat is 5%, which as a decimal is 0.05. Our sample size is 500 since she selected 500 cars at the tax office. I'll just go ahead and make a note that our alpha is 0.019. Starting with step 1, we will write our two hypotheses. Our null hypothesis always has the equal sign. So our null hypothesis is that P, I started to write mu there, but this is a test about the proportion. We're talking about percentages, so we need to make sure we're using the population symbol for proportion. So our null hypothesis is that P is equal to 0.10. Our alternative hypothesis, Sarah thinks that less than 10% of cars are pink. So less than 0.10. So that is our alternative hypothesis. That automatically tells us that this is a left tail test. We'll need that information when we get down to step 3. In step, our test statistic, using the formula that Z is equal to P hat minus P, all divided by the square root of P times Q divided by N, plug 5 minus 0.1 multiplied by 0.9, all divided by 500. We will round this to 2 decimal places to get a negative 3.73 as our test statistic. Now that we have our test statistic, moving on to step 3, We will determine our critical value and draw our rejection region. Our alpha is equal to 0.01, shade to the left. That is my rejection region. We need to go find what z value has a left area of 0.01. When I look at my statistics table, you're looking for 0.01, or the closest that we can find to that. We find 0.0099, that's away from what we need, which gives us a critical value of negative 2.33. So our critical, we put that into this picture, negative 3.73 is smaller than negative 2.33. So in step 4, we make the decision to reject the null hypothesis. And so since we are rejecting the null hypothesis of HO,
so again, in this example, we can see that we made the decision to reject the null hypothesis. So we are accepting the alternative hypothesis. I start my conclusion in step 5 with mentioning the significance level. We have a 1% significance level, and we are saying that there is enough evidence to support HA, which is that the population proportion of cars that are pink is less than 10%. In example 3, we have that Robert thinks a majority of students prefer chocolate candy over any other kind. Some RCC students are surveyed on this subject, and 63 say that they prefer chocolate, and the other 57 do not prefer chocolate. We want to test Robert's theory using a significance level of 0.05. So in this case, our population proportion is going to be P is equal to 0.50. And it is 0.5 because Robert thinks it is a majority, and a majority means more than half. And so that will come into our alternative hypothesis. We'll see that pop up then again. If P is equal to 0.5, then Q is equal to 1 minus 0.5, which is equal to 0.5. So we have P and Q. We are not explicitly given P hat. We are not given what our sample proportion is, but we can calculate it. We are given that X is equal to 63. X is the number of successes because 63 say they prefer chocolate over any other kind. But to find our N, our sample size, that consists of the 63 students that say they prefer chocolate added with the 57 who do not prefer chocolate. So we have to add both of those together to get our total sample size of 120. So now we can calculate our P hat, which is X over N. So we have 63 divided by 120, which gives us our sample proportion of 0.525. We are given that alpha is equal to 0.05. That's our level of significance. And so our level of confidence is equal to 1 minus C, 1 minus 0.05, which gives us 0.95. So we'll be 95% confident in our conclusion. Now we're ready to begin with step 1, where we write our hypotheses. Our null hypothesis is that the population proportion of people who prefer chocolate candy over any other kind of candy is equal to 0.5. That's the proportion of students who prefer chocolate. The alternative hypothesis, this is what Robert thinks. Robert thinks that it's a majority. A majority means more than. So he thinks the population proportion is greater than 1/2. He thinks it's greater than 0.5. So we know that this is a right tail test, since the inequality is pointing to the right. Step 2, we will go ahead and calculate our test statistic using the formula that Z is equal to P hat minus P, all divided by the square root of P times Q divided by N. Our P hat is 0.525, and from that we are subtracting our P of 0.5. Then we are dividing by P multiplied with Q. We have 0.5 times 0.5 there, and that is divided by our sample size of 120. We will round our test statistic to 2 decimal places to get 0.55 for our test statistic. Moving on to step 3, we will draw our rejection region and determine what our critical values are. This is a right tail test, so our alpha of 0.05, the entire 5%, needs to be on the right side of this bell curve. And that shaded region to the right is our rejection region. So we are looking for the z-score with a left area of 0.95. If we head over to our standard normal distribution table, the table with the z-scores, I have Z, LA stands for left area. A positive 1.64 has a left area of 0.9495, and a positive 1.65 has a left area of 0.9505. Both of those two left areas are equidistant from what we're looking for of 0.9500. And so we are going to average these two z values to find our critical value of 1.645. So our critical value is 1.645. Now that we know that, we are ready to take our test statistic of 0.55 and drop that into the picture. It's going to be rather close to the center since it's not that far from 0, and we see that it does not land in the rejection region. And so since this does not land in the rejection region, in step 4, we make the decision to fail to reject HO. And so since we have made the decision to fail to reject, we are not going to put the X on HO. We are going to put the X on HA. So now for step 5, we're ready to write our conclusion. Remember that we failed to reject the null hypothesis. So that means that we are rejecting the alternative hypothesis. So we are saying that there is not enough evidence to support the alternative hypothesis. And in this case, the alternative hypothesis was that the population proportion of students that prefer chocolate over any other candy is a majority, more than 50%.